Hello and welcome back to another season of the Oxford Online Maths Club. Hi, great to have you with us. My name's James. I'm a mathematician and administrator at the University of Oxford's Maths Department, and today on the show we're going to talk about factorisation. We're going to factorise some large numbers. But first, shout out to people who have joined chat just before we went live. I can see Aya's here, and hello to Herb as well. If you want to join in live chat as well, you can join in at slido.com/OOMC. We're using a separate website called Slido so that you can be anonymous if you want to, or you can put a little name if you prefer. Okay, I think I've remembered to unmute. You'll be aware there's building site noise in the background. I'm sure they make it louder around about 5 o'clock, but that's just how these things go. So I've got some announcement stuff on the screen. We've been off your screens for a couple of days, off your screens for a couple of weeks, sorry. So there's like a backlog of stuff that people have sent me that I'd like to tell you about. Yeah, I love these symbols, right? They're around the like circular forms of, and I'm trying to work out what the kind of matching is. There's a Mandelbrot set kind of like thing they've got going on over here. I guess that's maths. And then they've got an atom, so I guess physics, and is this like wiring, like a circuit board but round, and maybe some cogs and gears and things. This is a Jane Street summer school that folks at Jane Street mentioned to me. They are doing a summer school. We advertise a few summer schools on here. Here's one that you might be interested in called Wise, which you can find quite easily by searching for Jane Street Wise, or by following the link in there as well. Jane Street have also published a new puzzle. Before I told you about a puzzle involving hooks and things, and I think it's quite hard to explain what was going on there. But the new puzzle is easier to explain. There are two robots in a circle, and the robots are trying to jump to a target point in the circle. I should say that the graphic I've added here is not made by Jane Street. That's the art stream where we try and make art for things. Hello to people who are joining in chat. I can see some more people. I can see A and Anonymous, and I can see who's this joining now? Matthew. Hello Matthew as well. Okay, so there's a full range of anonymous people, people with an initial, which is semi-anonymous, and people with people who put a person's name in. I'm going to assume that is your name, but might not be. You never know who people are on the internet. That's one of the things about the internet. Okay. We're still running open days. I'm doing an open day in this building in 2 days' time, at time of recording, time of being live, and then another one online in this camera, I guess, in a week and a bit. So no booking required for that one. Update on further reading. I can't remember if I did this recently or after the last episode, but there's now some partitions notes. So I finally added these notes. They're a little bit different to some of the other further reading notes because they're written by someone else, and they've got problems in and challenges, and some of the challenges are really hard. So if you want to see some challenges based on some maths we were doing, several episodes ago, then you can find that on the further reading. Further reading is posted on the Maths Club website. If you've somehow found the stream without finding the website, hey, we have a whole website with previous recordings and links and further notes and stuff on the Maths website /r/club, where you can read more about previous episodes. Good. Okay. Let's run a poll quickly for how was your day. So I like to find out how people's day was. It's been a while since we did one of these. I wonder if today's a good day or not. I think I'm having a sort of 4-star day, he says, looking at the building works. I've tried to put some noise suppression on my microphone as well, so hopefully you're not getting as much building site as before. Possibly that makes it sound like a terrible online phone call. I'm not really sure. Let me know, I suppose, if I'm inaudible. So far, chat's on 3 and 4, and then both numbers are ticking. That's because the 5s are voting and changing both the numbers. Right, good, okay. I'm going to put some maths on the screen at the same time, because I've got to do some maths at some point. I've got some maths challenges for you, I suppose. I've got some bigger numbers. Here are the bigger numbers. I'm saying bigger numbers because in the thumbnail I've cheekily put the number 91, which we previously used as an example of something that is not prime. 91 looks prime, is not prime. I've got 3 more numbers which kind of plausibly could be, I suppose, not obviously not prime, but we're going to going to do not primes. Yeah, sure. So this is a new season in the sense that we had a little break for Easter, and that's how we reset our season counter, which is how we've made it to season 8, despite this being the 4th year that we've done these. We do 2 seasons a year. Some TV shows are like that. I guess most TV shows are not like that, which is why it's confusing. Wow, people are factorising super fast in chat. You see, but if you're watching at home, it's behind the polls. So if you want to let me know how to factorise these numbers, I think I'm interested in a method, because today I want to try and show you a method for factorising numbers that usually works. Hello again to other people. So who have I not said hi to? Oscar's here. Somebody called Burrito Man, who I suspect might be one of my students. And we've got this kind of like normal distribution of how was your day scores. I feel like 3.5 is kind of low. I guess people maybe are feeling the 2 weeks of no maths club. Let's see if we can get those numbers up. Right, so I have to always have the confidence that factorising numbers is what's been missing from your day so far. Okay, so when you first see this first day size 3,599, maybe your reaction, like me, is to think, is this a multiple of 3? I can see it's not even and it's not a multiple of 5. Is this a multiple of 7? That, by the way, is hard work. And if I trawl through all of that hard work of dividing it by 7, I guess 3,500 is a multiple of 7, and then maybe I know that 91 is not a multiple of 7, because 91 is. So, okay, not 7, it's not too hard. But then 11, I think I know a trick for 11s, multiple 11s, but they're going to have to keep thinking. I'm going to have to keep trying stuff. And this feels like a lot of work, and it's not very fun. But that is a method for checking. By the way, that is a valid method for factorising numbers. Just check for prime factors. And if you can find a prime factor, hey, you've made some progress on factorising it. Hello to an anonymous person in chat. Wasn't here in time for the poll because the bus was late. No, you were. No, wait, opposites. You were in time for the poll. Because the bus wasn't too late. Hooray, maybe that brings the average up. Good, okay. Yeah, so divisibility rule. Somebody's just posting now after the burrito post. There's a bit of chat lag today, isn't there? There it is. There's divisibility tests for some numbers. When you see them presented like this in base 10, this is called as particular divisibility tests. And people are still factorising numbers. There's a guess that this is about difference of 2 squares, and difference of 2 squares is one of my favourite things. So maybe a faster way to factorise that first number, rather than checking prime factors one at a time, is to spot something that's true about that number. To say roughly how large it is, perhaps. And I guess to say if it's P times Q with P roughly equal to Q, how big are P and Q? Let's get that right. How big are P and Q? Which feels like a sort of sensible kind of idea, I suppose. I mean, who says that P and Q, its prime factors, are anything like the same size as each other? Who says it's only got 2 prime factors? But we might guess this is a kind of starting point. Maybe it's really hard to factorise because its prime factors are both about the same size. And in that case, what you find is that its prime factors would be about, well, maybe you tell me, or maybe it's obvious, that if these things are about the same size, then P times Q would be about the size of P squared, or Q squared. And those would be about the same size as each other. In each case, those would be about 3,600. So P and Q would be about 60. And maybe that feels like a silly observation, but it's also quite good insight, I think, for working out, what's the kind of worst case scenario, right? As you're checking these small prime factors. Kind of worst case scenario is if it's just got 2 prime factors that are both quite large, small prime factors. Maybe that's what's going on here. And in fact, the way this problem's been set up is that this is in fact very close to 60 squared. Maybe this is something that you spotted straight away. that it's 3,600 minus 1. Well done if you spotted that. I guess that makes it a kind of gimmick or a trick question or something. This is 60 squared minus 1 squared. Once you've written it as 60 squared minus 1 squared, the difference of two squares, then you can factorise it by factorising the difference of two squares. So once you know it's exactly, no more approximations over there. Once you know it's exactly 60 squared take away 1 squared, you know that it's 60 take 1 times 60 plus 1. Which is why people in chat have got the answer, which is correct, 59 times 61. Okay, this is where I want to start, I think. Yeah, this is where I want to start for discussion of factorising these numbers. I'll let you do the second one. I'll give you a moment to do the second one in case, I can tell some people in chat have already raced ahead and they factorised my numbers. In case you've raced ahead, maybe you'd like to try this number down here. So I've got this kind of extra extension exercise way down here. It's a little bit larger, but you might like to give that a go. Okay, so if you're playing along at home, then you've done something like the number 4891. That's a little bit like 4,900, right? Just like this one was roughly 3,600. That was a little bit like 4,900. In fact, it's exactly 70 squared, take away 3 squared. So it's 67 times 73. And this kind of feels like cheating, right? This kind of feels like a shortcut right to the answer. It happens that the numbers I'm showing you on the board have got prime factors that are about the same size. Hi, Charlie. Yeah, sorry for the big number jump scare. It's there. Herb says, I don't think I've seen that number before, which, yeah, okay, good. You've seen the other numbers before, but okay. 7,031 I include because I want to be really clear that we're trying, we're looking for a large square that's a little bit more than the number in front of us. Let me say that again. If you're playing along at home and you want the large number, I hope you've copied down the large number because I'm going to zoom in again. Okay. The large number's there for a reason, don't worry. So 7,031, when you see that, maybe, it depends how many square numbers you know. I don't know square numbers up to there, so I guess I've got to get out a calculator. And this is about 83 or 84. It's sort of between 83 squared and 84 squared. I think I had to do some square root stuff on my calculator. And again, is using a calculator acceptable? I kind of think it might be. You can do something like 84 squared, take away. What am I talking about? You need to work out 84 squared, don't you? Okay, I'll let you carry on playing along at home. And I'm also going to read chat a little bit. So something I think I was doing when I saw the first two problems, before I'd really thought about it and planned out the session, something I was doing in my head was something like, for the first one, add 1 and get a square. For the second one, it's all about adding to get a square, right? So try adding 1 and that doesn't work, you don't get a square number. So try adding 4 and that doesn't work. So then try adding 9 and you do get a square number, you get 4,900. Over here, 4,900. And it was only when I was preparing this episode and getting stuff together that I realised that's a really silly way of doing things. I'm taking tiny little steps, just tiny little steps to look for a square number. What I should be doing is taking monster giant steps to go to the next massive square number. So here, instead of trying 7,031, try adding 1, is that a square? Oh no, it's not. And then try adding 4. These are tiny steps. And I need both the thing I'm adding and the thing I land on to be square. The big square numbers are really far apart. So if I need both of these things to happen, it's going to rely on these huge square numbers actually lining up. So really what I should do is skip through all of this working and just try looking at, is this going to be 84 squared? I hope that makes sense. It probably only makes sense if you were doing the same thing as me. If you were trying to add on small squares in the hopes that you'd see a square number, then this is quite slow because there's not very many large square numbers it could be. I guess as I'm going through all these small numbers like 7,032, 7,035, the only thing they could possibly be is 84 squared. And then eventually maybe they're 85 squared or 86 squared, but don't jump through the big steps of looking at 84 squared. Okay, so if this is squared, then I'm good. If not, then I suppose that I'll look at whether you can add a square to get to 85 squared. So said differently, what I'm going to do is I'm going to work out 84 squared, take away 7,031, and then I'm going to do 85 squared, take away 7,031. And then if that doesn't work, I'm going to try 86 squared minus 7,031, and then 87 squared, and so on and so on and so on. And I'm going to keep going. And in fact, for this particular example, good news, breaks straight away. This is 25, which is 5 squared. So we now have 84 squared, take away 5 squared. It's 7,031. But it didn't have to be this one. It didn't have to be the next square. It could be later on that it happens. Okay, which I think is then, yep, I is playing along as well. 89 times 79 is 7,031. Okay. Yeah, so Shrift asks kind of the opposite question to me. I said in passing something like, I'm going to keep going. So the kind of question there is, am I going to find something? And Shrift says, what if you can't do this? What if you can't split this up as? What if it doesn't work? So I suppose if all of these things I'm trying, 84 squared, 85 squared, 86 squared, 87 squared, what if these aren't a square number? So let's do a little bit of maths. Yeah, and I like that shortcut. I'm taking suggestions for shortcuts. I think in a second, but hold the thought. So let's say I'm trying to factorize a number. This is going to look a bit silly, but I'm going to say factorize a number n, which is, and I suppose it has to be a secretly a times b for some numbers a and b. I guess I'm imagining they're both primes, perhaps, not really important right now. Okay, so my method is something like start at the next square after n. I can turn that into maths in a second. We'll call that m squared. And the question is m squared minus n a square number? And then if so, if yes, I suppose, because it's a question, if yes, m squared take away n is x squared, and then we've got the difference of two squares thing that we've seen now a couple of times. But we also have a kind of backup plan. If not, or if no, try m plus 1 squared minus n, and then m plus 2 squared minus n, and so on. And this is not quite written out like pseudocode or like very rigorous mathematics. Maybe you can type this up at home. Yes, question in chat, which numbers can be written as the difference of two squares? Yeah, okay. So the question, I guess the question is, does this actually stop? If n is secretly a times b, can you say anything about when this algorithm, I guess when will it terminate? When will it stop? Or might it just run forever and never discover this kind of magical a times b thing? Yeah, and there's a catch, which people are talking about in chat, which I'm going to encourage. I'm going to encourage it by pausing a moment and letting you talk in chat. So I guess it's something like, I guess it's something like the thing you actually write down over here is m minus x times m plus x is equal to n. Now these A and B are secret. I suppose it might as well be the case. It might as well be a kind of secret, part of that secret, that A is the smaller one and B is the larger one. That doesn't really matter which way around it is, right? So maybe this happens, I guess this will happen. We'll see this happen for sure. For sure if this works. For sure if we get a situation where this is true and where this is true. And we know that n has this factorisation of a times b. So if this checks out, then we'll discover that factorisation. So that'd be nice. Yeah, and the good application coming through chat here. Products of two very large primes used in encryption. Yes, this matters. This is used in modern cryptography. It's an important part of RSA, and I suppose the idea is that this is difficult, which is reassuring, I suppose, if you find this sort of maths difficult, which I do, but hey, everyone finds this difficult. We're not really sure we've got any super really good, really fast ways to factorise numbers that are the product of two large primes. This is what we've got at the moment. Well, it's not all we've got, but here we go. We're going to do as much as we can in the next half an hour or so. We're limited by my understanding of modern factorisation algorithms, and we're limited by time. And I sincerely hope that it's the time that's the bigger problem. I hope we run out of time before we run out of my knowledge. Let's see. Okay. So this works, by the way. Maybe you've solved these equations if you're playing along at home to see that this happens. That happens if m is a plus b over 2 and x is b minus a over 2. So you have to keep going until you get up to, I guess I shouldn't be saying m plus 1, m plus 2 or something. I should be incrementing m and still calling it m or something. I don't know. Computer science, eh? It happens when m gets large, when m gets to a plus b over 2. Kind of average of those two factors. What am I talking about? Yes, I'm good. Okay. Yeah, if you're... okay. There is a minor problem which people are talking about in chat, which I'm now going to repeat back to you. Good job, chat. You've maybe noticed that if A and B, if one of them's odd and one of them's even, then the thing I've circled is not a whole number. And that's a problem because my algorithm so far is just looking at squares of whole numbers. Oops. So a way round that is maybe something that Olaf was saying is every odd number might have two odd factors unless it's prime. So you can do something like this. Let's dig into that a tiny bit. If our number is even, then it might be the case that it's just 2 times a large prime. That would be disappointing, I suppose. We should check that by, I suppose, dividing it by 2 and then playing with the remainder that we've got, the other number that we've got. If it's 4 times something, then it will be still even after we've divided by 2. I just don't like this case that it might have an even factor and an odd factor. But luckily for even numbers, we can divide them by 2 repeatedly until we get a problem with an odd number. So I think that needs to be at the start of my algorithm, which is something like first divide by 2 repeatedly until you're dealing with odd number. Or maybe I could change the rules of the game. Maybe I could say that n is an odd number. One or the other, I suppose, to change the rules of the game or to change what we're going to do when we see the number. I'm trying to do a thing about mathematics development here, how you discover, oh, but that's only an integer if a plus b is odd. And that means you either restrict or you try and deal with that and change things all the way through. Yeah, even factors are the easy ones to spot. There's only one even prime, which is a good thing, really. Hello, anonymous person who's just checked in. We're trying to factorise numbers. We've got this plan that will look for a big square number, such that the difference between that square and our target number is also square. And if we're dealing with an odd number that has two factors, we know that's going to happen when we get up to the average of those factors. That's the kind of square root target. Okay, so maybe the next question I want to ask then is something like, how long does this take? And that's a hard question, so let's put some more precision on it. I've circled this thing about how far we're going to go. We're going to start with a number like, in our examples it was like 60 and then 70 and then it was like 84. It's a bit like square root of n. So we'll start with a number like the square root of n, which I suppose is the square root of ab, and we're going to keep going until we get to a plus b over 2. So still a hard question, but now a little bit more tractable. If we start with a number like this, and we keep going up till we get to a plus b over 2. So we start with, that's got a name, that's called the geometric mean. You multiply the two numbers together and you take the square root. And this has got a name, this is the arithmetic mean. They're equal if a and b are equal. When are they very different then? This would be the bad case, right? The bad case is if we start with a number like this, we check, oh, is it 84 squared? Take away a square number? We say, no, you've got to check 85 squared, and then you've got to check 86 squared, and then you've got to check 87 squared, and keep going because a plus b over 2 is massive. Yeah. Yeah, so you know, Olaf says, does this mean you could check if things are prime like this? And the answer is yes, because you know how big the factors could possibly be. So you know after a while that the things you're getting out are not plausible factors. I can't quite think it. I can't quite do the answer in my head. I'm not sure I want to put it on the board. But yes, because you know how big the prime factors could possibly be. They're not that large. You won't be going forever until you think, I don't think I'm getting prime factors here. Yeah, if the number n is some prime multiplied by a power of 2, then I guess my algorithm for even numbers is first divide by 2 a lot and then feed it into the odd number algorithm. And the odd number algorithm is going to terminate and stop when it discovers the factorization of an odd number, because eventually it will get up to this kind of true fact. It will eventually get up to this square, and it will realize that it can write this difference to two squares. I guess the thing it will actually calculate is this, and after slowly incrementing this number, just keep increasing, oh my goodness, 84 squared, 85 squared, 86 squared, it will realize that, aha, this is exactly a square number. It will say, I've got a square number, brilliant news, I've discovered the difference from big square, take away the number that I was given, is this other square number, so I can write my number as the difference of two squares. This is kind of true by algebra. if you multiply all the squares. It's just true by algebra, and it's also kind of what's happening behind the scenes. If you know A and B, then you know what's going on. If you don't know A and B, then this line actually reads something like 84 squared minus 7031 is 25 squared, which is a little bit more mysterious, right? If you don't know what A and B are. I've now forgotten what A and B are. Oh yes, 79 and 89. But that's kind of what's going on behind the scenes, is eventually you get up to that one. Okay, yeah, so square root. Yeah, you just joined. Hello. So you've just joined, and this is a good time for a summary as well. We're trying to find a big square number such that the difference between that square and the target number is also square, because then, brilliantly, we can do a little rearrangement, like we did over here. A little rearrangement when we discover one of those things. A little rearrangement gives us a way to factorize that. 84, take away 5, 84 plus 5. It is a little trick for doing a factorization. It does feel a little bit like completing the square. I also feel like that might be enough burritos now. I think that's probably enough burritos. Okay. Maybe this step feels a lot like completing the square. Anyway. Okay, so this was an algorithm known to Fermat mathematician. You know, just keep trying larger and larger squares until eventually it all works out. This can take quite a long time if A and B are very different, because then the geometric mean and the arithmetic mean are very different. And I want to show you a refinement to this that was invented quite recently. So 1981, a mathematician called Carl Pomerance invents a kind of speed up mechanism on this. It's really good, and I'd like to show you how it works. Blam blam. Okay. Good. Okay, I need an example for this. So I'm going to try running the algorithm that we've got on the number 1207. I realised I haven't been very clear on what the algorithm does if you give it a prime number. It stops at some point, it gives up at some point. It realises that its search is fruitless because the potential factors have become too large or too small, and it stops searching. But everything I'm giving it today is not prime, so didn't think about that too much. Hooray! Okay, I'd like to factorise 1207, which is a number that is between, and I had to do this slowly, 34 squared and 35 squared. So the algorithm says something like is 35 squared, is this square 35 squared to take away 1207. And I go and do some maths, right? I go and calculate that, which is not too bad. 35 squared is 1225, take away 1207. I am reading off a little bit of paper. That's 18, which is not square. And so next, I say, well, maybe I can write it as a square, take away 1207. Maybe this one will be square. And 36 squared is a little bit harder to work out, but this turns out to be 89. Oh, there's a slight speed up if you're worried about how you calculate these squares and keep working out these numbers in this list. There's a slight cheat here, right? That each time I go from one line to the next, not cheating, but each time I go from one line to the next, the 1207 is staying the same, but the 3637 thing, all that's changing is I'm adding the difference between these two squares. So I need to add a 36 and then a 37, which is like a 70, adding 73. So this is 162. Once you've worked out one of them, it's easier to go between the lines than it is to get your calculator out again. If you like these things over here, these things form a quadratic sequence. because everything's quadratic, isn't it? But yeah, for the next one I'm going to add 75. There's a kind of pattern to these, a kind of sequence to what's going on. I'm also not trusting myself to actually do that. And we haven't got any squares yet. Again, if I get a square, then I'm done, because I can move it onto the left, move 1207 on the right, and say, aha, I've got 1207 as the difference of two squares. There we go. So this is kind of not going that well so far. You'll notice we don't have any squares. And in fact, this one is really hard work, because you have to keep going. This is also not square. You have to keep going until, I believe, I tried this at home. You have to keep going until you get to like 44 squared. You have to do a lot of work. So this is really slow. It's kind of a pretty bad case where the factors are not so small that we can spot them straight away, like 2 or 3, or using one of our tricks, like, is it a factor of 11? The factors are not so small that we can spot them straight away, and they're not so similar that root AB and A plus B are about the same size. There's a big difference between these things. So root AB is kind of a measure of 35, is where we start, and A plus B over 2 is the thing in that difference of two squares factorisation that we're trying to aim for. In this case, it's pretty big. And this happens a lot with kind of 4-digit numbers and upwards, that the factors can be a little bit alien and unusual, slightly larger primes that you don't recognise, but still be different enough that there's a difference between root AB and A plus B over 2. So, need an improved thing. Oh, do you want the square sequence again? So square sequence. The difference between the first line and the second line is, well, kind of plainly, 71. The difference on the left, look, to go from the top line to the second line, because all I'm changing is try a different square for the big square. What I've done is I've gone from 35 squared to 36 squared. So I've added 36 squared and I've taken away 35 squares. And then I giggled to myself a little bit, because like everything we're doing today, that is also the difference of two squares. And in fact it is 36 plus 35 times 36 minus 35, which is 1. So the thing that you add is just the number 71. And then something very similar happens on the next line, right? You add 36 plus 37, which looks a bit mad. I guess it makes sense as like you've got a 36 by 36. What is 37 times 37? Well, it's slightly more than 37 times 36, which is itself slightly more than 36 times 36. So it's adding a 36 and adding a 37, which is code for adding, I'm so bad at adding together small numbers today, 73. And then the sequence just sort of keeps going, right? At this point, I stop thinking about different two squares and I just go, it's adding 71, 73, 75, plus 77, so 314. That's a nice number. Good. Okay. That was all I meant by like quadratic sequence, or the idea that the difference between these lines is easier for me to calculate than the lines themselves. You know, that avoids me ever thinking in my head, what's 37 squared? Okay, it was enough work working at 35 squared the first time round. Yeah, there's some suggestions about odd and even numbers, which I like a lot. Chat is a bit laggy. I think it's just me in chat today, so there's also a little bit of moderation delay while I review and approve your chat message. One of those. Okay, here's the speed up, and this is kind of the only thing that I want to try and get through today, because I think it's a really good idea. It works like this. We're looking for a square on the right hand side. We haven't found one yet, but maybe we're not being creative enough, because if I look at these numbers we found so far, 18 is 2 times 9. You know, and that's not quite a square number. I'm not going to claim that's a square number, don't worry. But it's got potential. It's not a million miles away from being a square number. It's got some interesting 3s and 2s going on in here. 89, but that's just totally not a square number. That's some huge prime number. I'm going to write out the kind of stupid, I don't want the time sign. 89 is just 89. Maths is maths. 89 is 89. 162, that's kind of an interesting number. It's 2 times 81, which is 2 times... Now 81 is 3 times 27, 3 times 9, 3 times... Okay, it's 3 to the power of 4. And again, that's not a square number, but it's not a million miles away from being a square number, right? In some sort of like prime factorization way. And then 237 is horrible. I think it's something like 3 times 79 or something indescribable. 314, not much better. Some of these, the ones that use small primes, I kind of feel like there's something going on there. And in fact, here's the idea. The idea is to move slightly away from looking for something that's purely difference of two squares exactly correct. The idea is to look for something like this, where you can take two of these lines and multiply them. Okay, so I'm going to write out those two lines, including the stuff on the left. I'm going to take those two lines, including the stuff on the left, and I'm going to multiply them together. Oh gosh, all these numbers are huge, so don't worry, we won't be doing any actual sort of multiplication. That gives me something like this. 35 squared, take 1207, times 37 squared, take 1207, is equal to 2 times 3 squared times 2 times 3 to the 4, which is a square number. 2 times, little pause while I think about how square numbers work. That is a square number, right? Yeah, because I've got 4 and I've got 6 3's multiplied together. We've been talking about odd and even numbers a lot. The exponents there are even once you collapse everything together in the prime factorization. That's what square numbers look like. Square numbers always have even powers on the primes in their prime factorization because they came from something else being squared. When you square, you end up with even coefficients, even exponents upstairs. Okay. Yeah. Okay, good. So, we're not quite going to get 1207 as the difference of two squares, but we are going to get the following fact. We're going to get 35 squared times 37 squared. And then I'm going to put something like this, minus 2 times 3 cubed, which I think is 54, but I'm going to leave it like that so that we remember where it came from. This difference of squares is 1207k for some k. And that's putting it lightly, right? There's loads of stuff over here from first, outside, inside, last, from multiplying out the brackets. There's a 1207 times this thing, there's a 1207 times that thing, there's a 1207 times that thing on the outsides. There's lots of stuff, all involving the number 1207. But it is the case that this thing on the left, this difference of two squares, that we've sort of constructed out of what we had, this difference of two squares is a multiple of 1207. And it factorizes. It factorizes like this: 35 times 37 take 54. Oh, I kind of keep writing it like this. 35 times 37 plus 2 times 54 is 1207k. Okay. So if you're thinking about turning this into an algorithm, I have several bits of advice, but we're almost there. So here's the kind of wish and a prayer, I suppose. But if you work these numbers out, it might be the case that you get unlucky and one of them just is 1207 or is a multiple of 1207, and the other one is some random chunk which kind of matches up with the k. But maybe the factors of 1207 split into the two brackets. maybe this kind of splits the rock in half, and some of the factors of 1207 turn up on the left, and some of the factors of 1207 turn up on the right. That happens more often than you might guess, that the factors of 1207 end up in different brackets. Let's work out these numbers. That's a little bit of a horrible task. Luckily, I've got it on a bit of paper down here so that I don't have to multiply live. Yeah, so this is pretty good, I think, actually. You see this sort of suspicious thing, right? This expression that we've got has to contain, on the left somewhere, all of the prime factors of 1207. And on the right, there's 1207. One of the numbers is 1241. That's a bit suspicious, right? So what you asked to finish off is, do 1241 and 1207 have any factors in common? What's their highest common factor? Which some people write like this. Some people call it the greatest common divisor, and some people have a different notation for it entirely. But you might say, hey, maybe they've got no factors in common, and maybe this thing on the left contains all the factors of 1207. Although that doesn't look very likely, right? Because if this contained all the factors of 1207, then I mean, it's not equal to 1207, and it's not twice as big as 1207, so there's something going on here. This probably contains some of the stuff, and maybe that contains some of the factors. Neither is clearly a multiple of 1207, so I think there's some splitting going on. And in fact, the highest common factor of these numbers is 17, which is a factor of both of them. A sort of highest common factor trick. Oh, sorry, right, yeah, so chat, in chat, just prime factorize them and check for where those factors have gone. That is kind of acceptable, I suppose. I'm nervous because factorizing these 4-digit numbers, it might be easy. They might have totally different prime factors. They might be easier to split. It might be hard. Maybe it's not too bad. You start looking for prime factors on those numbers instead. They're actually slightly larger, which makes me nervous that we've kind of replaced our original problem with slightly larger numbers. But luckily there's this highest common factor trick to say, how is this thing on the left going to give me a multiple of 1207 if neither of those numbers are bigger than 1207? How's it going to do that? It has to give me the factors separately. So final answer, 17 is a factor, and in fact it is 17 times 71. Let's review this because I thought, think I lost everyone at some point. So we're going to do it again. The steps are as follows. Now that you've seen kind of where I'm going with this. We're looking for a square number on the right hand side. We haven't found one yet, but maybe we spot that. We can multiply 2 rows together, or maybe more than 2 rows, but let's start with 2 rows. And we can multiply 2 rows together to give us a square number. If we do that, then we will get what we're looking for, which is the difference of 2 squares. And okay, it's not just 1207 on the right hand side, it's 1207 times some stuff. But if we're lucky, the thing on the left will include the prime factors of 1207 in separate brackets. So we can look at them separately. We have this way to factorize the difference of 2 squares, which we're going to give it a try. Okay, so this sort of step is on a computer really easy to do, to take the difference and sum and then to just check if they've got any factors in common. So down here we've got our difference of 2 squares because we successfully built a square number by multiplying rows together. Okay, that's come with baggage. We've got this factor of k, and it's possible that k could be really unfortunate and end up ruining my lovely equation so that all the factors turn up everywhere or something. But it gives us a lead. It gives us something to look at to say, hang on, are there any factors in common between one of these things on the left and 1207 on the right? I realised that I haven't told you how to find the highest common factor or how you would do this kind of highest common factor check. And maybe this is nonsense, right? Maybe this is nonsense because if you don't know a quick way to find highest common factor, then how on earth are you going to find the highest common factor of these two numbers, right? Yeah. Do you know 17 is a factor of 1207? Yeah, okay. Oh, yeah, right, good, okay. I see what's missing. This is the missing ingredient that I didn't tell you. There's a way to find highest common factor without knowing any of the factors of the numbers. And it's faster. It's amazing. It's called, it's called Euclid's algorithm by a lot of people. That's not really accurate, but never mind. It's called Euclid's algorithm. Other people discovered it first. Algorithmy, who also invented algebra, knew this algorithm. Anyway, I'll link to the page. Euclid's algorithm basically says, I'm going to do a super quick version. How much of it do I want to teach you? I'm going to link to it. So the key idea, I suppose, is that if D divides 1241 and 1207, then D divides the difference. And more than that, much more than that. The algorithm is very clever and kind of does this repeated subtraction, which you also know as division, is sometimes called division algorithm. Anyway, to repeatedly look at the difference between things. The difference is smaller than the number, so this replaces a complicated problem with a smaller problem. But maybe you can see here that without factorizing these two numbers, if you're just looking for the highest common factor, then you can do this kind of detective game called Euclid's algorithm, where you go, well, if D divides both of these numbers, if they're both a multiple of D, then the difference between them is also a multiple of D, right? On the number line, the multiples of D come in regular chunks, and this is a certain number of chunks ahead. We should be dividing the difference, right? The difference is 34 in this case. I've dropped my stylus. Where on earth is that gone? There it is. Threw that really far. So it divides 34, which is a really small number, right? And even better, I can factorize 34. I know what the factors of 34 is. Euclid's algorithm actually gives you a way to kind of repeatedly do this. Yeah. Yeah. A detective theme with clues. Yeah, that does sound fun. So it's possible. Lots of things are possible at this last stage. It's possible that one of the numbers is just a huge prime. The other one is a massive multiple of 1207, and K is sitting there smugly being a huge number. There's like a multiple of everything on the left-hand side. It's very annoying. But perhaps it's not impossible to have a situation where the numbers are large, but it just so happens that the factors of 1207 are kind of spread out between the two brackets. Good. You've learned this algorithm before. It's a good algorithm. I haven't got very long. I think I'm going to quickly do. How much do I want to say about it? Keep forgetting it. Yeah. Okay. It's not too bad. Something you might write is that 1241 is one lot of 1207 plus this remainder of 34. And then you might say, well, now I'm looking at these two numbers, and I'm going to look at 1207, and that's some multiple of 34 plus a remainder of 17. This is me doing division in my head. It's very impressive, but my handwriting's so bad that you can't tell what I got. That wasn't convincing, was it? Okay. So this is called the quadratic sieve. There are some more clever ideas you can use to work cleverly to build a square number on the right hand side. The prime numbers are kind of building blocks, and if you're just trying to make a square, you just need the exponent to be even. The only thing you really need to track, if this is your aim, to build a square on the right hand side, the only thing you need to track is whether the things on the right hand side come up with exponents of primes that are even or odd. And you can do a little bit better than that, I suppose, if you decide in advance which primes you're using. So here we've built a square using 2s and 3s. And I saw people talking about the last digit in chat and thinking about, well, which primes appear on the right-hand side? Which primes appear over there? Which I suppose is like saying, I'm planning to square a lot of numbers on the left. So I want to know something like, is x squared minus n ever a multiple of p? Which is a bit like saying, is x squared ever n more than a multiple of p? Which is maybe a little bit more like saying, is x squared ever equal to n modulo p? If you know about modular arithmetic, there's this other way to write it. Which then people start talking about square roots and quadratic residues. I can't spell. Quadratic residues. To try and get that kind of insight into which primes are we going to see on the right-hand side, which primes are we going to work. Yeah, so the big number. Let's go back to the big number. 3 or 4 questions. So big number, where did that go? Oh, there it is. So this is a 129-digit number. It's called RSA129. It is semi-famous in the sense that it's one of a set of numbers which were constructed as a computational challenge. The idea is that a team of people multiplied together some enormous prime numbers and set them as a challenge. Please try and factorize these numbers. And that's been, in a way, a kind of measure of what the best algorithms are for factorizing numbers. If you invent a new algorithm for factorizing numbers, then you can test it on these ones, and there are some that people haven't factorized yet. When quadratic sieve methods were invented, they were used to factorize this number on the board, RSA129, which was the largest one of these challenge numbers to be factorized at the time, which is surprising because, I mean, people have made estimates of how long it would take to factorize a number that large using the previous methods. There's a security question here, I suppose. If all of your security depends on having a secret pair of large prime numbers, you've multiplied them together and told everyone the product, then your security depends on how fast people can factorize that large number, which is partly to do with computational power. It's partly to do with Moore's law and the speed that computers work at these days. But I would say it's mostly due to the algorithms that people are running, the ideas that people have had about better ways to factorize numbers, so that, just for example, with the thing we've been doing today, over here with quadratic sieve methods, you don't have to go all the way up to 44 squared. You can just do a couple of lines and then do something clever and a quick check along the side and discover a factor much faster without having to do all of the work to get to 44. It's like if, I don't know, this was maybe supposed to take 1 billion years to factorize, but someone finds a shortcut to do it in less than 1 billion years. There you go. The number was semi-famous all along. Yeah, people asking about odd and even numbers. I think I really dropped the ball on odd and even numbers. All of the challenge numbers are odd. In some sense, factorizing odd numbers is the hard thing. Factorizing even numbers, I mean, if you store them in binary, just cross off all the zeros on the end. Congratulations, you've taken out all the factors of 2, and now you have a binary number that ends in 1 because you crossed out all the zeros. Now you're trying to factorize an odd number. So kind of factorizing odd numbers is the hard thing, and factorizing even numbers is a tiny bit of chore followed by, oh, now we're factorizing an odd number. So kind of all the computational exercises, I suppose, are, here's an odd number. Questions in chat? Let's see. Ooh, hang on. So hang on. That says proof. If n is odd and n is a and b, one of a and b must be odd and the other even. So a plus b over 2 and a minus b over 2 are integers. Ooh, I'm suspicious. They look like not integers. Do you mean if n is odd and n is ab there? If n is odd and n is ab, both of a and b are odd. So those things are both integers. Yeah, I think that's what you mean. You mean both. Can this method we covered factorize any number not prime? If not, what numbers does it miss? It's a good question. It relies a little bit on this thing actually working. There's a small element of luck in there for the prime factors to split into the two terms. But you can collect quite a lot of data. If this doesn't work, you can keep going. 3 times 79 is a bit of a bust, but you could keep going to find some more examples that you could combine together into a square. And if you keep going, you might find a different one. You might get another chance. And in some sense, trying to take lots of shortcuts, each shortcut has quite a good chance of working. Trying to take lots of shortcuts is much better than just driving down the billion years long road. So I guess technically it works because in the worst case scenario, you could run this and it would just keep going until it hit a plus b over 2, I think. Even then, at some point it's going to stop. Yeah, how do you know how many lines to multiply? How do you know which lines to multiply? I haven't had time to talk about that at all, which is sad. In practice, people decide in advance which prime numbers they're going to be using. It's sort of maybe surprising you can be that greedy, but you don't want to be messing around with these factors of 89 and 79. You just want to say, oh, I'll just keep going until I find things that are only made of 2s and 3s. And it's a long billion-year road ahead, so faster than a billion years, I'll find some stuff that's made of 2s and 3s. There's an interesting question to say, if I show you two numbers, 2 to the A, 3 to the B, maybe 5 to the C or something. If I show you a bunch of these numbers, can you always combine together 2 or 3 of them? I've failed at the alphabet. If I show you these 3 numbers, can you always combine together some combination of them that multiply together to give a square number? The answer is yes, provided you've got more of them than you have primes. So I need one more, I think. And I need to remember the alphabet a little bit further. There we go. If you've got more of them than you have primes, you've chosen to look at the primes 2, 3, and 5. You've got 4 of these numbers. You've worked out their exponents. You can always find a subset of them that multiply together to give a square number. That's a kind of totally separate bit of maths, but is the reason that you have successes in here, that you can combine things together to make a square, and then you still have to get lucky down there to see if the factors split. And IMO, to finish this up, IMO has looked up the factorization of 129, I hope, or maybe implemented a quadratic sieve really quickly. So there, just to finish things off, is the answer to... it's kind of not really worked well in chat. The number's gone way off the screen. There we go. I have to scroll like this. We found a new way to break chat. There we go. One of them ends in a 7, the other one ends in a 3. For fans of last digits, 7, 3. Good. Okay, I think we're going to call it there. We've learnt to factorize large numbers by, if you like, looking at large squares that are slightly larger than your number until you find the factorization, or by trying to do a shortcut by building your own square, hoping that the factors split over the factors that you get from the difference of two squares. Okay, technical notes about which primes you might choose and how you build a square number out of the numbers that you've seen so far out of your data collection. I'll put those in the further reading, and there's a really good paper by Carl Pomeroy describing the development of this algorithm and the development of another algorithm afterwards, which is even better and has factorized larger numbers. Okay, good. I will see you same time next week for an episode where we've got a problem involving playing cards. But until then, how do I finish this show? How do I wrap this up? Until then, have a lovely evening, have a lovely weekend. We'll see you in 167 hours for another episode of the Oxford Online Maths Club. Bye.